Hi guys, this is Mrs. Gastler, and in this video we're going to be talking about some rotational kinematics. This is the basic stuff about rotational motion. We have already talked about circular motion and linear motion, and so we're going to be drawing on some of those concepts again. And so we're going to be doing, whoops, let me move that post-it. We're going to be doing some comparative stuff here. So I've already got some things written down. If you need to pause the video to catch up with that, or you don't want to write it down because you already know it, that's totally okay too, okay? The old stuff, this is review, is going to be on this side, and the new stuff that is oddly very similar is going to be on this side, okay? So to begin with, I'm going to draw you a picture. So we're going to be talking about a rotating object. For the picture that I'm drawing, because I'm not very good at drawing, I'm going to draw a circle. We're going to pretend that's a nice and very uniform, actually rotating disc, which I drew a much better one on my next page. Okay. And it's just going to be rotating, and it could be rotating this way, or it could be rotating the other way. Usually when we describe the direction that it's rotating, we use words like clockwise, or counterclockwise, counterclockwise, and that's usually as viewed from above, okay? And so we're looking down at the object that is doing the rotating so that we can describe the motion. Saying that it's rotating to the right or to the left is not specific enough, because are we talking about the top? Are we talking about the bottom? That could leave too much room for confusion. So saying clockwise and counterclockwise are your best bets for talking about the way something is rotating, okay? And so when we talk about rotation, and I'll talk about this again in a second. Whenever we're measuring rotation, we usually draw like an axis. Okay, so if we had like an axis here, this three-dimensional business. Okay, so our x and our y are going to be the flat ones. Here would be our positive x-axis, and here would be our negative x-axis. Positive y would be up here, and negative y would be down here. And this is three-dimensional now, right? So negative z is actually going to be down, and positive z would be up. Okay, so coming out of the page would be the positive z axis. And so when we're measuring the amount of rotation, we usually start measuring from the positive x, and we go counterclockwise. So if you read somewhere that some object rotated and it gives you some amount of rotation, unless it says otherwise, it means that it started here and it went that way, okay? That is useful information to know. Okay, start from positive x, go counterclockwise, unless otherwise stated, okay? That is a very useful piece of information to know, okay? All right, so let's get to it. So we've got this object, and we're going to be talking about its motion. So to begin with, when we talk about the position of an object, and maybe there's like a point P, or we're talking about the object. Now it looks like a smiley face. We're talking about where the object is going, or what it's doing. Before, with linear kinematics, we talked about the position. We gave it the letter X. We measured it in meters. Now we're going to talk about angular position. Angular position is going to be a Greek letter. You're going to learn a lot of Greek today, okay? It is the Greek letter theta. It looks like an O with a little curly line through the middle, okay? That is the Greek letter theta. I'm going to write that kind of down here. This is theta, in case you can't tell what I'm saying, T-H-E-T-A, theta. And we measure this in radians, which is a weird thing. And we abbreviate that because nobody wants to write out all those letters, to rad, okay? Radians. And if you're wondering, what the heck is a radian? Well, here's the best way I can explain it. Anytime you make a circle with a rope or a line, or you draw it, or you use objects, it doesn't matter what, you're going to have a circumference, right? Okay, your circle's going to have a circumference. And it turns out that the ratio of the radius to the circumference is always 2 pi, okay? It's always 2 pi. And if you were to measure out just one radius of the circumference, you will have gone an amount of a radian, okay? So this whole thing is 2 pi radians, and 1 radian will get you the arc length of 1 radius. So this is a radius, and this is a radius, and this arc length right here is a radius, and the amount that you have gone here would be a radian. Now we could convert that to degrees because we know that this is 360, and so there's a conversion rate there. So this is radians. Okay, so this is 1 radian, 2 radian, 3 radian, 4 radian, 5 radian. It's like 6.28, right? Okay, 2 pi is 6.28, so there's 6.28 radians in here. Okay, so I guess it's 1, 2, 3, and a little bit extra. Okay, 3.14 actually, right? Okay, and that just turns out to be true for all circles. So they're like, hey, that's really cool. Let's call it a radian. Okay, and so that is the unit that we're going to be using for theta. Okay, when you're doing calculations and you're crossing stuff out, radian actually is, it's like an invisible unit. It's kind of like 1. It doesn't actually have any other value than it's just radians. Okay. The next thing that we can measure that is like linear kinematics is displacement. So we were previously measuring that with delta x, and it was a vector because it had direction. This one is kind of a little bit nebulous with that. If you were in a different math class, we could probably do some directional stuff with it, but we're not going to now. So it's delta theta, same symbol, delta theta. So now we're going to sound like we're in fraternity and sorority. So just go in college now, okay? So delta theta, so we're talking about the change here. This is going to still be in radians, just like it was there, which is radian, again for the abbreviation. And just like before when we found the change in position, the displacement, there we did the final minus the initial, exactly the same here like this, okay? So if we want to figure out how much it rotated, maybe we know it was aligned this way and now it's aligned this way, we can find out how much it rotated. That's exactly what we're doing here. So the next thing we're going to be looking at is velocity. Angular velocity was v. Now you get to learn another Greek letter. This one is going to be omega. Now this one looks a little bit like a butt. I'm so sorry. It is, or a curvy W. It's called omega. This is a lowercase omega, in case you were wondering, or you've seen an omega somewhere else. These are all lowercase letters. The way you make it, it's not a W. This is a W. This is a W. Whoops, that's a weird W. W. It's not those, okay? It's really curvy on top, really curvy, okay? So that's how you make the Greek letter omega. So omega, okay? And we are going to measure this. You can probably guess, maybe based on these, it is going to be in radians per second, okay? Which is going to look like rad per s, okay? Which kind of sounds like we're talking about radiation, but we're not, okay? We're talking about rotational motion. Angular velocity. So the rate of change that we move something, we're talking about angular velocity. So before we found velocity by doing delta x over delta t. I hope you are not surprised to find out that angular velocity is delta theta over delta t. That shouldn't be at all surprising, okay? We're just dealing with Greek letters right now, right? Okay, so let's keep going. One more here. Acceleration. So acceleration, we had an A. We did meters per second squared. It shouldn't be too surprising. One more Greek letter, okay? This one's going to be the letter alpha. Looks like a fish, okay? Lowercase alpha, okay? Some people make it a little bit kind of weird on the end. I just kind of loop it around, okay? It's an alpha. Alpha, alpha, okay? Alpha. Okay, and this one, just like we did up here, is radians per second squared, which looks like radians per second squared, okay? So those are our rotation. Oops, I forgot the little thing. So we found the acceleration by doing the change in velocity. So hopefully you're not at all surprised to find that acceleration down here is the change in angular velocity over time. Okay, loads of fun. Okay, so this is just the quantities. Okay, so you can see there's kind of an equivalent quantity for the linear motion to the rotational motion, which allows us to talk about these things are going in a straight line and these things are spinning instead. Interestingly enough, you could have objects that are going in a line and spinning at the same time. And then that gets really complicated, and we probably won't do a whole lot of those, but we might need to think about them. Okay, so you might not be surprised, or maybe you are surprised to find out that since there are these quantities and when they change, there's relationships to describe those. And if you have some unknown pieces of information, you can find out relationships. You can do the same thing with the rotational quantities. And so we're going to look at those kinematic equations, and hopefully you won't be at all surprised to write down the equivalent rotational kinematic equations. Now, some of these are on the equation sheet and some of them aren't, but they're the same, okay? So we had all these equivalent quantities. The kinematic equations they're equivalent too. So if you are like, gee, this one's not on there, it is. Just change what it looks like, okay? So over here, our first one, we have VF equals V naught plus AT. I think on the equation sheet, it leaves off the F and it puts an X on everything like this, okay? It means the same thing. It just means that this only works in one direction. It doesn't, if you have it in 2 dimension, you have to make sure you split it up. Remember, you split it up for 2 dimensions, for 2-dimensional motion. Rotational kinematics is not exactly 2-dimensional motion. We're talking about the rotating motion, okay? It is 2-dimensional, but we're looking at specifically the fact that it's rotating, which is something different than 2-dimensional motion, okay? So we're going to take this 1-dimensional kinematic equation and we're going to make it into a rotational kinematic equation. And so instead of velocity, we have omega now, the angular velocity. So I'm going to put omega, the final angular velocity. We'll be able to find that by taking the initial angular velocity and adding to that however much the acceleration was times the time that it was accelerating, which is exactly the same as we were doing with linear kinematics. So all that stuff that you forgot in Unit 1, hopefully you're remembering now. This is kind of convenient, right? So it works exactly the same way. So if I'm rotating and I'm accelerating, I'm doing that angular acceleration for a period of time, that's going to add to my angular speed. That's all this one is saying, okay? So for the second one, this is the one where I have my change in position, my distance, however far I'm going to go in that one direction is going to depend on how fast I was going to begin with for however long I'm changing. And 1/2 AT squared. Now we see this one a lot without this one here because we start from rest a lot. And then 1/2 GT squared for whenever we've got a falling object, remember? And so what is that going to look like for a rotational kinematic equation? Well, instead of delta x, we have delta theta. Instead of velocity, we have the angular velocity. T is still the same. The half is still the same. Instead of linear acceleration, I now have angular acceleration, and T is still the same again. Okay, so they're like identical equations, but instead of regular letters, I have Greek letters, and instead of linear motion, I have rotational motion. So, but I'm still doing the same kind of information. So perhaps you can predict this one, because hopefully it's starting to seem a little bit obvious now what I'm doing here to write these rotational kinematic equations. Last semester we did labs to show that these equations were true, to find these relationships. And now if we were to do labs with these, with rotating objects, we would find the same thing. These labs are a little bit harder to recreate though, especially because I don't have the equipment to do it. Whoops, I just wrote VF, my bad. Okay, so instead of VF, I'm going to have omega F squared. And instead of V naught, I'll have omega naught squared. Still a 2. It's not alpha A, it's now alpha. And it's not delta X, it's now delta theta. This is the one that really sounds like it should be a fraternity. 2 alpha delta theta. Last one. These three, these three are definitely on the equation sheet. At least one or two of these are definitely on the equation sheet, and I'm not, I know this one is not, I'm not sure about it on this one, but it still works the same. So delta theta is 1/2 omega naught plus omega f times t. Okay. So if you're in a bind and you need to find an equation, you're like, I don't even want to look down on the equation sheet. You could just look at where those kinematic equations are, because they're at the very top of that list of equations on the sheet. Okay. So that is linear and rotational kinematics. This is probably the fastest review we've ever done for linear kinematics. But they're very similar things. So everything else that you've learned about linear motion and rotational motion are the same too. So all those graphs that we did, remember, let me write with a different pen so you can kind of see it. So all those graphs that we did where we did distance versus time, and we found that the slope was the speed. Yep, works the same way over here. So theta versus time, the slope is totally the angular speed, okay? And we did velocity versus time, and we found that the slope was acceleration, and that the area under the curve was the distance traveled. Works the same way over here. Angular speed versus time, the slope is, instead of A, it's alpha, and the area under the curve would be, I don't want to write D though, this is actually delta x, would be delta theta. And if I made a graph of acceleration versus time, which is pretty much, it's usually a flat line for us, and it's probably going to be a flat line here too. The slope doesn't actually mean anything. We'll write question mark, question mark. It's actually something called the jerk, and people who make roller coasters care about it. And we don't care about the slope over here too, but the area under the curve would be the change in speed. Whoops, this is change in omega, and over here it's change in speed. Okay, so they have, again, it's so similar the way these things are set up. It's just that this is going in a straight line and this is an object rotating. Okay. Some other things are going to work a little bit differently on account of the rotating, but this first part is very similar. So hopefully this one isn't too bad. Okay, but there is something else we have to talk about, and that is how these two things are related to each other. So we have the linear kinematics and the rotational kinematics, and they're very similar in how they function, but how are they related to each other? Okay, so that's our last thing here. So we're going to pretend that we have an object here, and we'll call it point P, okay? And we're going to pretend that this is an R away from this center line here that this object is rotating about, and we'll say that it's rotating this way, okay? Okay, which would be viewed from above is counterclockwise, okay? And so it's going to be going like that, and maybe it goes all the way to this point, so it's going to go through some angle theta right there. Okay, over time, and maybe it's rotating constantly, and so, or maybe it's accelerating, or maybe not. I don't know, but we want to talk about some differences about some linear motion of that point P and the rotational motion of the entire object. Now, every point that is on this thing is rotating at the same rate, because the whole thing is, I mean, it's like, you know, particles, they're stuck together, it's a solid object, so that's what's happening. But points on the object are not necessarily moving with the same linear motion, and that's because of where they are. And we knew that, though, because of circular motion. So I'm going to make a little note here that this is kind of like circular. Let me try and write actually where you can read it. Circular motion. We're going to have to think a little bit about circular motion right here to be able to get these things correct. Okay. So let's talk about the speed of this object. So So let me bring out this thing that it's moving on. So it started here, and if it ended here, and it followed this path here. So let's call this length S, and this theta right here. If the angles are small, and we talked about this when we were talking about circular motion, if the angles are small angles, then S equals R theta. Okay. If you need to see this again, I want you to come find me. S equals R theta works for small angles and not a whole lot of other things. Big angles, it doesn't work, but it kind of does. It still kind of does. Sort of. Okay, so, but we're going to use this. Okay, so S equals R theta. Okay. So remember how V equals delta X over delta T. Okay. Well, in this case, our particle is moving from point P. We'll call this initial and this final. Okay. And when it does this, the distance that it moves is that S. Okay. Let's call it delta S for now, just in case it changes. You know, maybe it's going smaller or faster. There's some people moving some desks around in my classroom over there. They're making noise. And hopefully you can see that if it moves some delta S, and R isn't changing because it's a solid object, then delta S, what's going to be changing is that delta theta. So I'm going to put this in here, okay? And so this is going to become R delta theta over delta T. And we were just talking about this thing right here, delta theta over delta T. Where did my paper go? Is right there. It's omega. So this is going to become R omega. So what we know then is that the relationship between the linear velocity of the object at that point is the same as, or we can find it by doing R times omega, the linear velocity times the angular velocity. Sometimes people call the angular velocity the angular frequency, and that's okay. So if you see anything that says angular frequency, it might be the same thing. Okay. So when we talk about acceleration, there's actually 3 accelerations we have to talk about. And the reason for that is because this object is doing kind of some circular motion. This point, not the object. Well, the object is rotating, but the point on it is actually doing some circular motion. So when we talked about circular motion, we only focused on uniform circular motion. And because of that, our object was going at a constant velocity the whole time, and so we never had a change in velocity to talk about. So we know one of the accelerations. So let me draw a circle here. Okay, so here's our point P, and it's going around, okay, through some angle. Now we know one of the accelerations, and that's going to be that centripetal acceleration. And you know that centripetal acceleration, the formula for that is on the equation sheet, and that is v squared over r, okay? But there's this other acceleration now that it could be speeding up, so that linear speed, that is in the direction it's along, they call this, because it's along a tangent line, they call it the tangential speed, could be changing or is changing, could change because it's rotating, and if it's experiencing some angular acceleration, then the tangential speed could change. So there might be what's called, they call it the tangential acceleration. They call it ATAN, okay, tangential acceleration. There we go. Okay. So the tangential acceleration, it is dependent on the object rotating faster, and the centripetal acceleration is just from the fact that it's rotating. So even if it doesn't accelerate faster, it's still going to have the centripetal acceleration. Okay. So the tangential acceleration, if we look at that one specifically, the tangential acceleration is going to come from a change in the linear speed. So that's going to come from a change in that linear speed over time. And we can stick that one in directly. So the linear speed, r isn't changing again, right? So we're just going to put in v equals r times omega. So we'll put in r delta omega over delta t. And delta omega over delta t should be somewhat familiar to you because delta omega over delta t, we just wrote down, it is alpha. So the tangential acceleration is r alpha, which has a very similar format to this right here. So this, in fact, we might kind of call it a linear acceleration, but it's really more of a tangential acceleration. But it's the equivalent of a linear acceleration. And then this is our angular acceleration. And so that, let me draw it on my diagram. So that, if my object is going this way, my tangential acceleration is going to be right here. So we'll call that a tan. And my centripetal acceleration is going to be directed toward the center. We'll call that AC. And if I wanted to see how that one was related, I just have to put in this v for that v. So v squared would be r omega squared over r. All right, so this r is going to cancel one of those r's out and leave the other r there. So just the omega is squared. And so this is the centripetal acceleration. So this is the acceleration it feels toward the center that makes it go in the circle, and this is the acceleration it feels in the direction that it's going that makes it speed up or slow down. I guess it would be against its direction if it's slowing down in that rotation, okay? But together, this brings the third acceleration, which would be the total acceleration. And since those are perpendicular to each other, it really ends up looking like a triangle, right? So we've got a tangent. If we put them end to end, we've got AC right here. So a total is the hypotenuse. How do you find the hypotenuse of a triangle? Well, it's the square root of one plus the other, okay? And we don't really need to find that. I don't know that you're actually going to have to find that, but understanding that that's how they're related is really useful, okay? So these are the different accelerations that you might find. I'm going to circle some of these. This one right here, and this one right here, and that right there, and this right here. Those are the important things on this page right here. And that's about all that we could possibly talk about with rotational kinematics without talking about what's making it rotate faster or slower. And that's going to be the subject of the next video. Make sure if you have any questions, especially if you want to understand anything more about this S equals R theta or what a radian is, that you ask your teacher. Thanks for watching.